So we are told that the IQ scores. So this is established as being population. We are told it is bell-shaped. That's why we can use the empirical rule. Okay, so all these go together. So the IQ scores are population, bell-shaped, which means I can apply the empirical rule. You're going to see me write this many times moving forward, that this particular IQ scores a squiggle, which means the distribution is normal. We haven't talked about normal, but the bell-shaped, and always followed by like a ordered pair, x comma y, but that's not it. It's the mean, which is mu, and the standard deviation, which is 18. So please get used to moving forward to this notation. Again, what does it means? Particular distribution can be x, it doesn't matter, whatever. In this case, we have IQ scores. They are normal or approximately normal with mean of 100 and a standard deviation of 18. Okay, so the first question, part A, is asking us to find the percentage between these two. Okay, so what I'm going to do is I'm going to calculate all three possibilities, meaning mu plus 1 standard deviation with minus, in other words, mu minus standard deviation, 100 minus 18, and comma, 100 plus 18. We're going to calculate in a minute. Then the other one, mu plus or minus 2 sigma, which will be 100 minus 2 times 18 and 100 plus 2 times 18. And finally, mu plus or minus 3 standard deviations, 100 minus 3 times 18, 100 plus 3 times 18. So then I know that this is that 82, and this is 118. So I found that this is, as we know, it's 68%, is 95%, and 99.7%. So I already have the answer for part A. It's 68%. Now they're asking us this. This is not a tricky question. So this is part A and this is part B, but very interesting, very nice. So we are talking about, we don't know this word yet, but I'm going to say for now bell-shaped. I know that between 82 and 118, this area is 68%. In part B, they're asking us, what is the percent less than 82 or greater than 118? So that percentage is here and here. Their sum. So can anyone tell us what is this area? Always remember the entire area has to be 100%. Total, always 100%. If 100% I subtract 68%, how much will this be total? 32%. So the answer for part B is what is in the tails. These are called the tails. Tail to the left and another tail to the right. So that is part B. Now they're asking what is the percentage for greater than 154. I have no idea where 154 is yet, but I will. So I will determine my numbers here. So what do I have here? So I have 100 minus 36. And is that 54? 36, 64. So that's 64, and this is 136. Okay, what about this one? So 3 times 18, So added to 100, how much? 3 times 18. So 150. This is my 154 that I'm looking for. And this I don't even care that much. But let's determine it, right? So it's 100 minus 3 times 18.
46.
46 indeed. Very good. Excellent. So then I'm going to draw another bell-shaped distribution. Here it is. This piece, right, this number right here is 46, and this number is 154. And I know that this inside area is 99.7%. Careful now, they're not asking us for the total in the tails. No, they only want this piece. So from 100%, I subtract 99.7. So from 100, I subtract 99.7, and I divide this number by 2. Okay?
So it's 0.15 then?
0.15, exactly. So this piece is 0.15, and this piece is 0.15, but they only want one tail. Very good question. Thank you for that. Okay. I'm sharing the screen. Okay. So say it again.
I was saying, are we still taking requests for 3.2?
Yes.
This was actually the question I was going to say.
Oh, awesome, awesome, awesome. So, okay, what am I entering here? I'm entering 68 for the first part. I'm entering 32 for the second part. And I'm entering 0.15 for the last part. Very good question. Thank you so much for asking that. Is there anything else you would like to look at here?
I had questions about standard deviation, but solving that problem kind of answered them for me.
Okay. Who was that?
Michael?
Very good. Thank you, Michael. Anything else?
I have one. 12, please.
Which one?
12.
12. I just wasn't sure. I thought I heard 12. Okay. The weight of an organ in adult males has a bell-shaped distribution with the mean of this and the standard deviation. So I stop there, and I take my notes. That's the first thing I write. I write that the weight appears to be normal with a mean 325 and the standard deviation 15. Use the empirical rule to determine the following. About 95% of organs will be between what weights? Okay. What percentage of organs weigh? Okay. B, 310 and 340. Okay. Okay, part C, less than 310 or more than 340. And what percentage of between, okay, 295 and 370. Now, since this is very similar to the previous one, can you just choose one of these, A, B, C, D? So we can move on? Because it's, which one?
A.
Okay, about 95% of will be between what weights? Okay. So we are told, I'm going to stop sharing. So we are told that this is bell-shaped, approximately bell-shaped with a mean and the standard deviation. So we want to determine this situation. We want to determine this number, and we want to determine this number.
Because it's 95% that they're asking for, would it be the mu? Is it plus or minus the 2
yes.
sigma? I think
yes, very good. A mu plus 2 sigma. That's it. So all I have to do is determine Very good. Who was that?
That was Gabe.
Thank you. So 2 times 15 is 30. 325 minus 30 will be 305. And 325 plus 30 will be 355. So the answer to 95 in this case will be between 305 and 355. Is this okay?
I think that's right.
Any questions? I'm going to share my screen. Yes, anything else? I'm sorry, I didn't mean to interrupt.
I said none at all. Good answer.
Okay, very good. Thank you. So now let's take a look at, I had the data set somewhere here for you. I can close this. I don't need this. This one. No, not this one. I wanted to go back for just 1 second to the way Wendy's McDonald's wait time. And I want to go back to the histogram. I want to, yeah. So this is the histogram for Wendy's. And this is the histogram for McDonald's. Which of these two, this one or this one, you would like to wait in line for? So should I go to Wendy's? Because I don't want to wait. So the idea is not to wait that long, right?
Probably Wendy's, because more of the graph is. Oh, I'm sorry.
You are not sorry, because you are correct. You are
Oh,
correct.
okay.
Because this is so far out, so skewed. I may end up waiting this much, right? The dispersion of this graph is much lower than the dispersion for this graph. So the people at McDonald's, or just the location has too many people coming in at almost at the same time. Maybe it's not the staff, but it's just they're overwhelmed. Okay, so you will, according to these two, you will definitely want, this is less dispersion, so you will definitely want to go to Wendy's versus McDonald's. Absolutely, based on what we have here for this particular location. Maybe other locations have a different situation. Okay, so that's what I wanted to say about that. And now I would like to go to section 3.4. I know we have like 10 minutes left, but maybe we can finish one more section. So 3.4 deals with measures of position and something called outliers. Okay. So the measures are presented. So first of all, out the z-score. And I got a question about the z-scores, and I want to talk about it as soon as possible so we can have it answered. So what is the z-score, first of all? It's the distance. So the z-score characteristic to every observation. For each observation in the data set. So every observation, for every other observation in any data set, I can determine its corresponding z-score. And what is it? Is the distance from the mean in terms of standard deviation. The z-score will tell us how many standard deviations away from the mean is a particular observation. So here's the notation and how we calculate it. So it's z. So it's x, a particular observation, xi, x1, x2, x5, minus the mean divided by the standard deviation, if we're talking about the sample. Same method Same formula, but different notation if we are talking about the population, because I have to replace x bar by mu and s by sigma. So this is for the population. And I do have an example. Here it is, and I'm going to add it in. I'm going to copy the information right now. So here's an example, and then we'll directly go to my lab math to answer your
Sorry,
colleagues.
can you share that formula again?
Yes.
Thank you.
Yes. So the z-score for this particular observation, so zi if you want. So z1 corresponds to x1, z2 to x2, etc., etc.
And I would just be like the number of observations, right? What would the I be?
From 1 to the last one.
Okay. Thank you.
Thank you. So I is from 1 to last. Okay, so we have the mean height of feet of males 20 years or older is 69.1. So the mean height, 69.1 inches, with a standard deviation of 2.8 inches. The mean height for females, so I'm going to call this 1. So this is for males, and this is for females now. So the mu2 for females, 63.7, with a standard deviation of 2.7, of course, inches. And this is for females. Perfect. Data is based on information such and such. Who is relatively taller, Kevin or Candace? Kevin has a height of 83, so I'm going to say here x1 is 83 inches. And Candace has 76. So I'm going to say x2 equals 76. How will I know which one is higher? Which one is taller relatively to their cohort? Is determined for this z1 and for this z2. And then I will compare the z's. So this will be 83 minus the mean divided by the standard deviation. Same thing here. It will be 76 minus the mean divided by the standard deviation, which is 2.7. So I will put the information in my calculator. Don't forget parentheses around the top. Parentheses 83 minus 69.1 and divide by 2.8. And the other one, parentheses please, 76 minus 63.7 and divide by 2.7. So the first z is 4.96 and the other one is 4.55. Please remember moving forward that also z has a distribution, extremely important distribution with 0, 1. We're going to talk about this a lot. It's called standard normal. Standard normal, z, those z-scores, if you graph them, all the z-scores in any data set, not with 5 observations though, please, then they will look normal. They'll be approximately normal. They have to be with the mean 0 and the standard deviation 1. So if I draw that, here's what happens. The mean is always 0. 4.96 is here, and 4.55 is here. So this is Z1 and this is Z2. So which one is taller relative to their group or cohort, in other words?
Male.
Yes, absolutely. So this is higher. Higher z-score, taller relative to his group versus Candace relative to her group, of course. Okay, so now we have, I want to finish with that particular problem in 4. If I find it. Okay, here it is. So it was in 3.4, if I remember correctly, it was problem 3. So let's take a look. Problem 3. A highly selective boarding school will only admit students who place at least. So highly selective boarding school will only admit students who place at least 1.5 standard deviations above the mean. Okay. On a standardized test. So that's my page 5. So I'm going to copy the information first. So at least 1.5 times the standard deviation above the mean. Okay. Good. That has a mean of, okay, so it's 100, and with a standard deviation of 20. So these are the standardized, so again, the scores. Normal with 120. What is the minimum score that an applicant must make on the test to be accepted? Very good question. Thank you. I'm hoping to finish it in 1 minute. So the minimum. So now we are told that the z-score has to be 1. Oh, let me stop sharing. Sorry. So we are told that the z-score has to be minimum of 1.5. So then, knowing the formula that the z-score is x minus mu divided by sigma, and replacing the z-score by 1.5, replacing mu by 100, and sigma by 20, I'm solving for x. Solve for x. This is a proportion. It's over 1. First, I will cross multiply. So x minus 100 must equal, or just multiply both sides by 2, must equal this. So this is 30, right? So 15 times 2. Add 100. So we get, if a student does not have a minimum score of 130, which means 1.5 standard deviations away from the mean, if the score is less than 130, the student is not admitted. If the score is above 130, the student will be admitted.